guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So since reactants and products can be in different states and reactions can also occur at different pressures, the enthalpy of a reaction can often be different. But when all reactants and products are in their standard state at 1 atmosphere, the reaction enthalpy is called the standard reaction enthalpy, and it's given this small 0 at the top of the delta H, and this signifies that it's at a standard state. So the standard state for a gas has a pressure of 1 atmosphere, so this is for a gas, and for a solution, it has a concentration of 1 molar at 1 atmosphere. For a pure liquid or a solid, the standard state is the pure liquid or solid. And the standard state for an element is its most stable phase at 1 atmosphere and the temperature of interest, which is usually 25 degrees Celsius. So pressure is 1 atmosphere. Temperature is usually 25 degrees Celsius. And this is for an element of interest. And this is the most stable phase. So most reactions are given in their standard state, so you'll see this form of the delta H or enthalpy value. The standard reaction enthalpy for the formation of 1 mole of a substance from its elements in their most stable form is called the standard enthalpy of formation. Enthalpy of formation. And this is given the value delta HF for formation with this circle at the top. And this is also in the units of kilojoules per mole. And so as an example, using graphite, which is the most stable form of the element carbon, and gaseous hydrogen and oxygen to form ethanol, let's write out this reaction. So 4 carbons plus 6 hydrogens plus oxygens gives 2 ethanol, which is a liquid. And so the reason why I stated this is graphite is because it's the most stable conformation for the element carbon. And so the delta H of this reaction, the standard enthalpy of reaction, is negative 555.38 kilojoules. And the delta H of formation of ethanol, since we're forming it from carbon, hydrogen, and oxygen, right? So you write that out by putting the ethanol in brackets. So this is the delta H of formation of ethanol, and it has a value of negative 277.69 kilojoules per mole. So this is a very typical example where there is a standard reaction enthalpy for a particular reaction, because things are in their most stable state, and we can also have a standard enthalpy of formation of the final product. So by definition, the standard enthalpy of formation of an element in its most stable form is 0. So the reaction of creating ethanol from carbon, hydrogen, and oxygen requires standard enthalpies of formation, or the standard enthalpy of the reaction, right? But what if the bond enthalpies are not available? In that case, one can calculate the standard reaction enthalpy, or the delta H naught of the reaction, by calculating the standard enthalpy of formation of all the products. And then subtracting the standard enthalpy of formation of all reactants. Okay, so now let's relate these in an equation. So the delta H of the reaction is the sum of the delta H of formation of the product minus the sum of the delta H of formation of the reactants. So let me show you an example of this so you can see it. So what if someone asked you, what's the standard enthalpy of combustion of methane, CH4? So combustion is always when you burn something in oxygen. Make sure that it's a balanced equation and you end up with carbon dioxide and water. So this is a standard combustion equation for methane. So now you can go to the back of your textbook where you can find tables of the delta H of formation of different compounds. And make sure that everything is in the standard state, so you can see that this is a gas, 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 liquid. Make sure that these are all in their standard states and that the reaction is balanced. So I put the coefficients of 2 in front of the O2 and the H2O to balance the reaction. So now using this equation, let's try to figure out what the delta H of the reaction is. So you can get the values of the delta H of formation of each of these individual components from a table in the back of your textbook. So then, the delta H of the reaction can be written as 1 mole of the delta H of formation of carbon dioxide, since remember you do products first, right? So let's do CO2, and you have 1 mole of it, plus 2 moles of the delta H of formation of water. So here, again, it's really important that you balance your equation because you have to remember to put down the number of moles before the delta H of formation value. So from here, we subtract 1 mole of the delta H of formation of the reactants now, so methane, CH4, plus 2 moles of the delta H of formation, I'm sorry this is getting all squished now, of oxygen. Alright, so I barely fit it in. So these are values that you found in the back of your textbook, and so I'm just going to substitute those in for you right now. But again, these are values that are standard, so you can find them. Negative 394 kilojoules per mole, or on an exam, usually your professor will give you those values. 2 moles times negative 286 kilojoules per mole, minus 1 mole times negative 75 kilojoules per mole, plus 2 moles times 0. So right here, the reason why the delta H of formation of oxygen is 0 is because an element in its most stable form is 0. I mentioned that before, right? And so this guy is just a value of 0. When you add those up, you end up with negative 891 kilojoules. So this is an exothermic reaction, right? So let's go over what we just did. When you don't know the enthalpy of each individual component, you can't use Hess's law, you can't use the bond enthalpies, and you have to use this particular equation, where you go and find the individual standard enthalpy of formation of the products and the reactants, so that by summing it up, you can actually get the delta H of the reaction. And so this is a way in which you can also find enthalpy values that are in the standard state.